Thank you everyone who is joining us today for part 2 of our Introduction to Blockchain series. This one is going to be a technical workshop to go along with part 1. I believe George will paste the recording from the previous workshop that occurred on Monday this week, as well as if you're not a member of the Discord community, George will also be pasting the invite link to that as well. And just to keep a reminder that we do have the second Stellar workshop occurring next week on July 7th. And the week after that will be part 1 of the Polygon workshop, which will be occurring on July 12th. So be looking out for those. And if you can attend as usual, they will be recorded and put onto your YouTube channel the following day. And so as usual, if you have any questions throughout this workshop, be sure to ask those in chat, and we'll be sure to get those answered at the conclusion of the slides. But until then, Laurence Kirk, you should be good to go.
2 more. Should we just wait 2 more minutes to?
Oh, of course.
To get everyone in.
Perfect.
But yeah, I've sent the link to the session from Monday, which was kind of more of a theoretical introduction to blockchain, but this one should be a bit more technical, using Remix, which is an in-browser development environment. So if you want to go ahead and get that up, let me try and find a link. There we go. For anyone that wants to follow along, if you click the link I've just put in chat, you should be able to try and do that there. Is there anything else people should have prepared, Laurence, if they want to follow along?
No, that's all you need. Yeah, just need Remix.
Perfect.
Great.
Yeah, okay, I'll keep admitting people in. We'll get started in 60 seconds. Hey, Harry, how's it going?
Good, thanks, George. You?
Good, thank you. Good, thank you indeed. Yeah, so anyone that's not in the Discord, be sure to join. But yeah, I think I put the link in the chat there. And Danny, do you want to do the next 2 upcoming workshops as well?
Yes, I'll get those posted in there.
Sure, I can post them.
Okay, yeah. So as mentioned before, that for the people that are just joining, our next 2 workshops will be occurring over the next 2 weeks. On July 7th, we have part 2 of the Stellar Intro to Stellar workshop, and this one is how to get started developing on Stellar. And then on July 12th of the following week, we will be having the Polygon workshop, which is an introduction to Polygon. So George did just post those sign up links in the chat. So be sure to sign up for those if you think you'll be able to make it. And should we be good to go, George?
Yeah.
Awesome. Well, Laurence Kirk, you should be good to go now. Okay, thank you, Daniel, thank you, George, thank you, Encode Club, for inviting me, and to everyone to coming to this second session of Introduction to Blockchain. If you didn't come to the first one and you don't know about me, I am the CEO of Extropy. We're a blockchain consultancy based in Oxford. We write smart contracts, we do security audits, but we also love to do community education and teach people about blockchain and what a fantastic piece of technology it is. So it's great to be able to do that again this evening. So today I'll just mention our proof of stake briefly, because someone asked about that in the last session, but I will do that very quickly. Then we'll move on to looking at Ethereum and smart contracts and designing for decentralization, but this will be fairly brief. And then we'll go into the language Solidity, and we'll start using Remix and writing a smart contract. And I'll finish up with, if we have some time, just a few tips I have for people who are involved in hackathons, which I think are fairly useful. And then we've got time for questions. I probably won't monitor the chat. It's quite difficult for me to do that. So I'll come back to the questions at the end. But if there's anything important, then yeah, do feel free to interrupt me. Okay, so briefly about proof of stake, because we spoke about proof of work last week. So proof of stake is a different consensus mechanism. There are many different types of it and derivatives. For example, you can get delegated proof of stake. But generally speaking, blocks will be produced and maybe attested to by actors called validators. these validators will have been given a time slot in which to produce a block, and they are randomly assigned to do this, and there are various mechanisms to do that. Different blockchains will do this in different ways. The important thing is that the validators in proof of stake must provide a stake, and for example in ETH 2.0 this is 32 ETH, so they need to have something to lose. So whenever you're looking at blockchains generally, it's good to look at the crypto economics behind it and look at people's incentives and how the protocol manages people's incentives and aligns those incentives to ensure good behavior. So this, with proof of stake, the incentive is around the stake that the validators have provided. And the validator can have their stake slashed if they behave maliciously, if they do something wrong, such as trying to propose 2 blocks at once, or test 2 blocks at once, or maybe if they go offline, they will also lose rewards. So very different from proof of work. You don't have this complex calculation that you have to do. Therefore, you don't have to spend a lot of energy. So there's not the economic incentive around energy that we have in proof of work. But for that reason, we don't have the environmental cost that we see with proof of work. Okay, so that's briefly proof of stake. I mentioned that because someone asked about that last session. So let's talk about Ethereum. So the major step after Bitcoin, really, the next one was Ethereum, often called the world computer. And the nodes on Ethereum, as well as doing the normal blockchain protocol stuff, they also have a virtual machine running on them. And it is the state of this virtual machine that is the state of the system. That is the state that we are coming to consensus about. And the state in Ethereum changes because of smart contracts. These are small applications that are run and will change the state of the virtual machine. Every node in the Ethereum network runs these smart contracts. So if someone runs a function, it will be run on every node at the same time in this network. So everybody does the same calculation. They have the same starting point, so they should get the same endpoint because they've run the same piece of code. Just an interesting thing to have a look at, let me share this, is this visualization, a live visualization of Ethereum. So this shows, it's quite a fun thing, it shows transactions happening. So this is a live view of the Ethereum mainnet, and it shows transactions happening. So on the left-hand side, we have some of the major projects on Ethereum, such as Tether, Uniswap, MakerDAO, etc., producing transactions. These are all coming across the right-hand side here, and they are waiting to be put in blocks. Now, it's slightly confusing because the things on the right-hand side, when they're mentioning GWay here, they're not actual blocks yet. They're just the transactions being lined up in terms of the transaction fee that they are prepared to pay. So they've bundled together some here that are prepared to pay 23 GWay, and at that point a block has been produced, and there's another one that's been produced and has gone off and has been part of the network. So it's quite a fun visualization, but it gives you an idea of how many transactions are around at any one time waiting to get into a block. And as you can see, there is a huge queue. So these ones at the top here, they're paying, say, 13 GWay as a transaction fee, but there are a lot of transactions that are not prepared to pay that much. So you can see here a huge amount of people waiting down here who are not prepared to pay that much, hoping that they'll get put in a block. Okay, let me stop that one and go back to my, now I've lost my screen share. Oh, there you go. Go back to my slides. Okay, so that's an interesting visualization tool. It's worthwhile bearing that in mind, that you have all of these transactions happening all the time and being picked up and put into blocks about every 12 to 15 seconds. Okay, so let's talk about smart contracts. So these are the applications that run on Ethereum. They're just small pieces of code that run in a virtual machine. the Ethereum virtual machine, the EVM. As I explained last time, the environment is highly restricted for various reasons, such as security and determinism. The contract itself can be thought of as having three parts. There is the code, the functions that you want to run. There is the state of the contract, so some variables in your contract. And optionally, the contract can also have a balance of ether. And this ether is controlled by the contract itself. Even though they're called contracts, they don't have any legal meaning unless that is set up outside Ethereum. And they're written in high-level languages such as Solidity, and then they're compiled into bytecode, and it is that bytecode that is put onto the EVM and runs in the EVM. Okay, and the process of creating and running a contract is that, say Alice wants to create a smart contract, she will write that, and I'll show you an example of that in a second, and then she submits that, deploys that to the blockchain. So that contract, the bytecode of that contract, is put into a transaction, and that transaction is then passed onto the blockchain. And it passes around all of the nodes on the blockchain until everybody has a copy. And then it is picked up by a miner and put into a block, and that block will get passed around and everybody will run the transactions in the block. Once the transaction containing the bytecode for that contract is run, then that virtual machine on that node will have that contract available, and people can then call the functions within that contract. If someone else, such as Bob here, wants to call a function in the contract, he will send off a transaction representing the function he wants to call and the parameters he's passing into that function. And similarly, that will get passed as a transaction and go all around the network, so everybody gets that transaction. Again, that will get picked up and put into a block. That block will get passed around the network, and then once the virtual machines get that block, they will then run the transactions in that block in the order that they appear in the block. Now, there's an important distinction to make in the types of functions that we have in Ethereum. And there are some functions that we call view functions, and these functions are read-only functions. So these functions just want to read some data from the contract. They don't want to change the state of the contract. They don't want to write anything to the contract. They just want to read it. Now, these are treated very differently, because if you think about it, since every node in our system will be synchronized and will have the latest state of the contract on that node, if you want to read some data, you don't have to create a transaction and come to any consensus about reading that data. You can just go to one of those nodes and ask for the data, ask it to tell you the value of a variable, for example, from that contract. So for view functions, if Bob wants to find out, run one of these functions that just reads data, all he has to do is contact a node, and that node can then give him back the data that he wants. They can run that view function for him and send him back that data. And he will get that data back straight away. So he will get that synchronously. If we look at the, sorry, I missed a slide, but if we look at the other option where we have a transaction where we're writing data, then that is quite different. Once Bob has created his transaction saying what he wants this function, what function he wants to call, and the parameters he's passing to that function, he sends it off to the network. And then he doesn't know what's going to happen to that transaction. I mean, he has to wait for it to get mined. And as we saw with those transactions queuing up to get included in a block, that could take a while. We don't know what fee he will have been prepared to pay for that transaction. So he will send off his transaction, and then really he has lost contact with it, and it becomes asynchronous at that point. And he has to wait for the block to get mined and for that transaction to get picked up and to be run on the nodes. And once it's run, the only way he will find out that what has happened with that transaction is if either he then queries the blockchain again, or he can use something called an event, which is something that he can subscribe to, which is effectively a callback, which will tell him that something has happened in his function. It will send back maybe the results of something. So that is the distinction we have to make between view functions, read-only functions, and then normal transactions which write something which change the state of the blockchain. Okay, as I mentioned last time, we have restrictions on what we can do in our contracts. So gas restricts the amount of computation we can do. Determinism means we cannot use random numbers, for example. And if we want to get data into our contracts, we have to use third parties called oracles, and we ask them to push data into the network in the form of transactions. I won't go into anything more about oracles. The languages available in Ethereum, the most popular one, the one we'll look at today, is Solidity, but there are other ones. I guess the next most popular one is Viper, which is rather like Python in its syntax. There are some new ones such as Bamboo, but the main one, the one that most people use, the one that looks more like, I guess, JavaScript, is Solidity. That's the one that is really pretty much the most mature and really has the most resources available for it. So it's a good place to start. Okay, I'll just quickly mention about designing for decentralization. I mentioned this last time. The problem if you have a game in a smart contract, such as rock, paper, scissors, because of the transparency of transactions, if you're playing a game, all of the players in that game will be able to see every move. So if Alice here plays rock as her first move, Bob will be able to see what she has played, and as his move can play paper and will therefore win the game, and the smart contract would pay out. It's not much of a game. If we want to improve it, we can do something called commit reveal, where we obfuscate what Alice is doing by using a hash function and wrapping up her move in a hash. So she sends the hash of the value into the smart contract. This is the commit stage, and Bob also sends a hash of his move into the smart contract. And then at the reveal stage, they reveal in plain text what their move was. And the smart contract can take those, and by applying the hash function, it can check that that was the move that they made in the commit stage, the move that they committed to, and then can verify those moves and award a prize accordingly. This is still not perfect. You can still get around this, but it is a step in the right direction. It just goes to show the kind of thinking you have to apply if you want to play a game or write a game in a smart contract, and the differences between writing applications on centralized systems as opposed to decentralized systems. Okay, so let's get on with our introduction to Solidity. So Solidity is, in syntax, is quite easy to follow language. It's statically typed, so that's great for me. I like statically typed languages. It supports inheritance if you're comfortable with object-oriented programming. We can use libraries with it. We can define types in there, and has many other features that you would expect in modern high-level languages. But having said that, there are many features that are missing. So one of the ones that most people come across quite quickly are things like string manipulation. So there is no inbuilt support for that. We have to rely upon libraries for that at the moment. And there is the documentation for Solidity is pretty good. There's a link there to the read the docs for Solidity. So they will pretty much answer any questions that you may have. But also Solidity has been around a long time. There are lots of resources out there to help you learn Solidity. If you're interested, we have a website. I'll put a link to it later, where we've got some tutorials around Solidity. There are lots of other websites that have tutorials and games to play to help you learn Solidity as well. So it's a good language to start with if you're developing smart contracts on Ethereum. Okay, so let's jump into that. I need to share enough the screen. I need to share my browser.
I've just put the link to the Extropy Foundation in the chat as well, Laurence. We have two questions. Do you want to maybe take them quickly now?
Sure, yeah.
Yeah. So Harry's asked if there's a way to prevent a contract from receiving Ethereum.
Okay. In theory, there isn't really. If someone's determined to send some ether to your contract, they can. It's a bit of a convoluted method that they have to use to do it, but they can do it. There are means you can put functions in your contract to reject people who do ordinary methods to send ether to your contract. But if people are really determined to do that, then there is a way that they can do it by effectively destroying a contract, calling a self-destruct on a contract, which they can do that and make that then send ether to your contract. So if you're thinking about security, and you definitely should be when you're writing smart contracts, always be aware that if people want to, they will be able to send ether to your contract. And there have been a number of vulnerabilities and a number of problems caused by people ignoring that fact and not realizing that that can happen. So yeah, yes, they can. Was there another question? Or?
Yeah, the other one was if you could kind of expand a bit more on what you mean by determinism.
Okay, yeah. So determinism means that when we run a function in a smart contract, we want to make sure that the resulting state of that contract is exactly the same for every node in our network. So that is the same, every bit of data in our contract is exactly the same. So in order for that to happen, we have to restrict how our contracts work. So as I say, we can't have random numbers because then contracts running on different nodes may produce different numbers. But also that means we can't have floating point arithmetic either, because different machine architectures may implement floating points differently, and you can get subtle differences. So the Ethereum virtual machine has imposes these restrictions so that the final state after a function runs we can be 100% confident it will be exactly the same no matter which node that this contract runs upon. Yeah, so that's what I mean by determinism.
Awesome. Thank you very much. And there's just one quick one from Felix. He's asked if a contract can hold ETH in escrow.
Yes, you can write. Yes, you can write special escrow contracts, and in fact, there are some good libraries for that as well. So OpenZeppelin have some example libraries of escrow contracts. Yeah, so you could set up a contract and give it a balance of ETH, and then control how that is moved by whatever else your application is doing, and maybe that contract is an intermediary. Yes, is an escrow between various users in your system. So yeah, and there are libraries to do that. Okay.
Awesome. Thank you. That's all of them.
Okay, so let's start by having a look at Remix. So this is Remix. When you open it, it usually brings us a default another contract up as an example. So there's some example code there, but I'm going to write a contract called Score. So I've gone to that. But before we get onto that, let's have a look around the parts of Remix. So on the very left-hand side here, we have some icons that allow you to choose what you're going to do. So the top one is your file area. So it allows you to create and save contracts that you're writing and to choose them, to edit them. The second one down is the Solidity compiler. You can choose the version. So let me choose. I'll go back to 7 actually. You can choose whichever version you like for that. And you can choose the language if you wanted to. There's an intermediate language called YURL which you can use instead, but we're going to use Solidity. I would recommend putting it on auto compile. This means that every time you make a change to your contract, the compiler will run, so it gives you instant feedback. It's very useful. You can enable optimizations. So this just means your code will run more efficiently. And there's a button there to compile your contract as well. The next icon down is once you've compiled a contract, you will want to deploy it to a blockchain. So this is the icon and the area you need to do that. And it gives you at the top here a number of choices of the environment where you can run your contract. Now, it usually only has one JavaScript VM choice at the top. I'll explain why. There are two there in a second. And when you're starting out, the easiest thing to do is to use this JavaScript VM choice. And the reason is that this is just a little blockchain, a little in-memory blockchain that is just running within your browser. It's not connected to anything else. So it's a great blockchain to use for testing. And it provides you with some accounts, with some fake ether. You can see here, you have some accounts that have 100 ether. Sadly, you can't actually use that on the mainnet. But yeah, it's a useful area that you can try out. You can deploy your contracts to this. It won't cost you anything in the real world money. And you're not actually deploying, and you're not interacting with anything else. So it's great for testing. If you want to move on, you can do things such as go to Injected Web3. What that does is it looks to your browser for plugins, such as MetaMask. So if you choose Injected Web3, that will then try to interact with the blockchain that your MetaMask plugin has chosen. So if you have MetaMask installed in your browser and you have that connected to, say, the Robston test network, then when you deploy a contract from Remix, choosing Injected Web3, it will go to the Robston test network. And then the final one, you get the Web3 provider. This allows you to specify a URL. So if I choose that, it will ask me for an endpoint. This is a URL of a node on a blockchain. So this could be a node I'm running locally, as in this case, or it could be a node running on the Ethereum mainnet or on the Ethereum testnets, or it could be a node provided by a network provider such as Infura. So with this, you can then interact with the Ethereum mainnet if you wish. But I'm going to stick with the JavaScript VM. The reason it has two options here is because of an update that is about to happen on Ethereum. We're currently on the Berlin update, and we are moving to London. London has been rolled out on some of the test networks, and it will go onto the main network shortly. But it's a major update to Ethereum, so that's why we have the choice. Just to explain, once you have your contract here, this is where you choose your contract. If you have a number of contracts you've compiled, there would be a number of them here, but I only have one. And then you can hit deploy, and that will deploy your contract to the environment that you've chosen at the top. So currently I've got, I'll just explain this. The other thing here on the left, this plugin manager allows you to choose other plugins. So there are other things that you can use, for example, a debugger. We have some other useful tools such as Mythex. This will help verify your contracts. There is Hardhat. This is a IDE, so this will interact with that if you want to interact with Quorum network, etc. So lots of interesting, useful plugins. I'm only going to use the three I've mentioned here. So this is the files, the Solidity compiler, and the environment. Okay. So what I've got on the right-hand side here is the area where I edit my contract. Below that is a command line. This is showing what's happening on the network that I'm connected to, so on the environment. So if I do something, if I deploy a contract, I will get some update happening at the bottom here. But this area at the top, the main part here, this is where I write my contracts. The top line, I'm just saying what version of Solidity I want to use. So I said I'm going to use anything above Solidity 7, or between 7 and 8 actually. I could change that. I'm going to in fact change that to be greater than 8. we'll see that then, yeah, then when that will get recompiled. The second line down, this is just a comment. It allows you to specify a license. You don't have to put this in. If you don't put it in, you get a warning, that's all. And then the next line here, line 4, we have a keyword contract. So this is where we define our contract. So I'm using the keyword contract, and I give my contract a name. The name of my contract is score. Now, the file that I have this in is score.sol. That doesn't have to match the same as the contract name. That's what you call the file is up to you. You can have more than one contract in the file, but if I save my score.sol to my hard drive, I can do that through this tab here. Then that's why you get to that's why you need to give it a name. Okay, so I have a valid contract here. It's empty, but the syntax is correct. You see that we've auto-compiled it, and we get a green tick here on the left-hand side to say there are no errors. If there was an error, if I do something like that, you see that we get a red mark here to show where the error is, and on the left-hand side here we get a red number, and down here on the bottom left we get an explanation of what the error is. Generally speaking, you should look at the errors, look at the warnings that the compiler gives you. The compiler is your friend. It's going to help you write your contract, so do take note of what it's telling you. Okay, and because I got auto-compile on, when I fix that error, it compiles it back. We get the green tick again. Okay, so we've got our contract called score. We can go ahead and deploy that. Let me do that. So that happened very quickly. So I pressed deploy. Almost immediately we got this green tick here, which says it's deployed it to the VM blockchain. If you're not using the in-memory blockchain, if you're using one of the test networks or the main network, it wouldn't happen so quickly because we have to wait for the transaction to get mined. Because this is in memory, this happens very quickly. Also, then once it's deployed, we see at the bottom left here, we have the contracts that we have deployed. So it's deployed my score contract. It tells me the address it's deployed to. And it has a little drop down. Because I don't have any functions in there yet, it doesn't have anything useful in this drop down. We'll see in a second when we have some functions in our contract that they will get more information. I'm going to delete that because that's not much use at the moment. Okay, and just to say, even though I've deleted it there, that just deletes this display. It's still available in the blockchain. Things we put on the blockchain always stay there. Okay, so there we have our initial contract. It's not much use. So let's give it some state. So I'm going to have a variable in my contract, and the point of my contract is to keep track of a score. It's a bit contrived, but that's what I'm going to do. So I'm going to add a variable here, and I'm going to call it score. I told you it was a statically typed language. Here I'm declaring the type of this variable. So I'm declaring it as an unsigned integer because the score is going to be a positive integer. I've put in here 256, which gives the size of this variable. You can have different sizes. The default is 256, so if I don't put that in and put just uint, that's what we'll get. But I prefer to be explicit, so I'm going to put in uint 256. So we've got a green tick on the left-hand side. That means the syntax is correct. Now our contract has some state, which is great, but again, it's not much use because we could deploy that, but we can't read that state. We can't change that state. So we really need to do something more useful with it. So let's create a function to read that state from our contract. So we'll create a function called getScore. Now there is an easier way to do this, but I want to show you how to create a function to get the score. So let's do that. If I just do that in a kind of a naive way, and we'll get some errors. So we'll get the errors and we'll see what the compiler is telling us. So it will tell us what we need to fix. But what I want to do in this function really is to return the score that I have there. So the idea of this function is to return the value that is in this variable. But the compiler is telling me that I've got some problems. I'll come to the first error in a second. The other thing I need to add here is I need to say what this function is going to return. We're a typed language, and the functions need to know the types of their return values. So I have to make explicit what I'm going to return from this function. So I'm going to return the uint256. So I need to put that in here. Okay. So now it knows that the type of the value I'm going to return, but it's still got a problem, and it's telling me I don't have a visibility specified. And this is something that applies to all functions and something we need to specify for all functions. And we have a choice about the visibility. And what the visibility means is really around where can this function be called from, and how can we restrict how this function can be called. And the choices we have are, the one I'm going to use here is, oops, in the wrong place, is public, and it goes up here. And this is the most permissive of the visibility modifiers, or the choices we have for visibility. This means that this function can be called from externally, from outside of this contract. So perhaps from a website that is calling this contract. It can be called also internally, because it can be called from within this contract. We could say that this is an external function. What that would mean is that we can call this function from outside the contract, but not from within the contract. Now, if you're wondering why you'd want to do that, it allows us some optimizations if we do that. So if we know our function won't be called from another function in our contract, making it external is a way to optimize the contract to some extent. Also, it's a good idea to have it very clear, very explicit in your contract, what the kind of the API is of your contract, what your contract looks like from the outside world. So what functions are you exposing externally, and what functions are internal. But I'm going to leave it as public for the time being. That's the most permissive. The other choices we have, you can also have it private, which means it will not, if we use inheritance, then it can't be called from inherited contracts. Okay, so that's the visibility modifier. We have a table about those on our website if you go to that, explaining all of those. So that's the best place to look for those. So now we have a function where we can get the score from our contract. So great. We do have another warning here. So this yellow bar here means it's a warning. So let's have a look at that. The compiler is helping us. So it's telling us that this can be restricted to a view contract. So if we remember what I was saying earlier about view functions and write functions, this is a read-only function. We're just reading the score from our contract. And so the compiler is telling us that we can restrict the type of function. So let's make this a view function, and then that will keep the compiler happy. So now the compiler knows that this function is only going to read the contract. Okay, so that's great for returning the score. So now we can read the score from our contract. We've got a green tick, so we can deploy it, but it's not much use still because we can't change the score. So let's put a function in there to change the score. So we'll write another function. They all start with a keyword function. I'm going to call this one set score. We have to pass in a parameter for our score, so we'll pass in a new score. Often it's traditional that you put an underscore in the input parameters to functions. You don't have to, but if you see this in contracts, that's why you get that. It's just done as tradition. So we're going to pass in this new score, and we're going to update the score from that. So I'm going to say score equals new score. And once again, if we go back to our compiler, it wants to know the visibility of this function. So I'm going to make that one public as well. So there we have a simple function that allows us to change the state of our contract. So that's probably a good point to deploy it. So we've got a green tick, so this is compiled okay. So let's move to our environment and deploy that contract. Did it very quickly again, but you can see on the left-hand side here, we have the contract, and now we have two buttons, and the buttons you get in this area represent the functions in your contract. So, and they are color-coded. So the view functions are colored this sort of gray-blue, and the write functions, the normal transactions, are colored orange. So if we run the view function, you see that, so I have to move this up a little bit. You saw something happen in this output area. So you saw that there was a call made and that it went to a particular function. And then the return value from the function is given here. So it says it's returning a uint256 and the value it got back is 0. If it returned multiple variables, then you would get multiple values here. And this first value here, this 0, is the index of the return value. So the first one that came back, it came back with 0. That's what we expect. We expect it to be 0 to begin with. Our other function here, our setScore function, allows us to input a value. So let's input a new score. If you want to do it on a separate line, you can click this up/down arrow. You don't have to, but it may make it easier to input variables. So we input what we want to transaction to be, sorry, our new score to be, and then we can click this to create the transaction. Now, again, this happened very quickly. It ran our transaction and mined it. We get a green tick to show that that worked okay. If the virtual machine threw an error, it would tell you here that it had thrown an error. It would tell you there was a reversion in the function. But it didn't, it ran okay. This hasn't updated. We need to rerun this function if we want to check the score. But if I rerun our get score, we can see that the value has now changed. So the state of our contract has changed because of the transaction that we sent. Okay, how are we doing for time? Okay, we've got a little bit of time left. So I'll just quickly mention something else about functions that we need to know, because this is fine as far as our contract goes, but we probably don't want just anyone to be allowed to change the score in our contract. So the way the contract is written at the moment, it would mean that anybody could interact with the Ethereum blockchain. They could run the setScore function, provide a new score value, and that would update our contract. And that's probably not what we want. We probably want to restrict that in some way. And we probably want the idea of that some users in our on the blockchain will have special permissions, will have special rights in our contract. And then if the users are not special, then they won't have those rights. So we probably want to give certain users on the blockchain permissions for our functions. And the way we identify users on the blockchain is by their Ethereum address. If you look at the output area at the bottom here, when I made this call, it was saying that a call has been made from a particular address. In fact, more perhaps better is the one where we had the update function. So the transaction here, where it's also saying there's an update the address here is the one that ran that transaction. And if you look, that is the one that we have specified in the account area here. If I ran a transaction from a different account, you can choose a different account here, then you would see different values here. So it will be effectively a different identity running that transaction. And you see that the amount of ether that this account has gone down because as I deployed contracts and as I ran transactions to do set score, this took a little bit of ether away as a transaction fee. It took a little bit of ether away for the gas needed to run those transactions. Okay, but to go back to what I was saying, we want to restrict the functions. So we're going to do that according to the address of the person on the blockchain, so the Ethereum address. And address is a type in Solidity, so we can create a variable of type address if we want. And I'm going to set up a special address, which I'm going to call the owner. Okay, and I'm going to say that this contract has an owner. I'm going to put the address into this variable, and they're going to have special permissions on this contract. In fact, I want them to have special permissions about getting the score. About setting the score. I don't care about getting the score. I'm going to let anybody run that function, but I'm only going to let my owner set the score. And the way that we do that is via something that is called a modifier. And this is a special piece of code that we need to write to restrict who can access a function. So we started off with the keyword modifier, and then we need to give it a name. So I'm going to call it only owner. And then we need a body for our modifier. Now, there are different ways we can do this. I'm going to do this quite explicitly. There are better ways to do this, but I'm doing all this in a very explicit way just to show you the syntax and how this works. But I'm going to add in an if statement here, and I'll explain about this in a second. Okay, so this is my modifier. Now I know the syntax is a little bit confusing, so let me explain what this does. Effectively, this is a piece of code that is going to check who the person is that is trying to run my function. And it's going to restrict who can run my function only if they are the owner. Now, when your contract runs, when you have a transaction, you will have a variable available to you in your contract called msg.sender. This is the address of the person who started this is the address of the person who is running this function. Now, there are some nuances around this. I won't go into those, but you can think of this as the person who is running the transaction. And what I'm going to do is I'm going to check the address of that against the owner that I have in my contract that I will have set up previously. What this does, this piece of code here, is says if the person running the function, running the transaction is the owner, then they can continue. And it goes to this underscore here. And effectively, this is where the function is placed. You can think of this as wrapping around the function. So if it passes this test, it goes onto this line here, which is telling it to go to the function. And we have to specify this in the function also. So I'm going to add that here. So I'm going to say only owner. So now when someone tries to run this function, it will go to this modifier, it will go through this test. If it passes the test, it will carry on with the function. Otherwise, it will just return, it won't run the function. So now we have restricted who can run this function to be only if they are the owner of this contract. But we have another, and that's fine. We could have a function here to set the owner of the contract, but we would come across a problem in that we would want security about changing the owner of the contract. Obviously, if anybody could change themselves to be the owner, then this restriction would have no meaning. So the function that we would write to change the owner would also need an only owner modifier on it. But then we would have a chicken and egg situation, which would be, how do we set the owner in the first place? And the way that we do that is via means of a thing called a constructor. Now, if you know object-oriented coding, you will be familiar with constructors. These are functions that run when in this case, a contract, or with object-oriented code, a class is first instantiated. And it's similar with Solidity in that the constructor is a special function that only runs when the function is deployed. In fact, the constructor is not put on the blockchain in the bytecode along with the rest of the contract code. It is run as part of the deployment, but then it is not needed ever again. So there's no point in adding it to the blockchain. It is thrown away. So bear that in mind. The constructor only runs at deployment time, and then it is not available in your contract. But what I'm going to do in my constructor is allow the constructor to set up who is the initial owner of the contract. So I'm going to set up the owner variable here. So I'm going to say the owner is the message sender. So what I'm saying here is I'm saying the person that called the constructor, which is what's the address of the person, the address that is held in message sender, that person is going to become the owner. So this sets up the first owner of our contract. And then from that point on, we could have a function that would allow us to change the owner. But if you're wondering who is the owner, who is the person running the constructor, who is msg.sender when our constructor runs, well, that is the person that deployed the contract. So the deployer of the contract is the person who will be set up as the initial owner of the contract. And then from that point on, they could perhaps pass ownership over to other people in the contract and change the permissions in the contract in more elaborate ways. But this is a way of kind of bootstrapping the whole thing and allowing us to set up an initial owner. Okay, so that covers a few things. I'll just quickly mention events because I haven't mentioned those. We can set up events as well. As I explained earlier, we use events to get some feedback from our contract. So they can be thought of as log statements as well. It's a way of logging information from our contract, but it's also a way for applications to receive values back from functions that are not view functions. If we call this function, we get a value back straight away to an application. If we call the setScore function, we don't get a value back. Even if we said here, returns, uint256, that would not come back to the person calling that function. So we have to use an event for that. And you can then listen for events on a particular contract. So I can set up an event, which I'm calling score set. That's the name of the event. And I'm going to pass into it a value. So when I change a score, I'm going to say what the new score is. And the syntax for doing that is that we use the emit keyword. So we emit events and we give it the event name, and then we put in the value. So here it is going to be the new score. So if somebody was listening to the score, listening for the score set events in the contract, that person would then, once this function runs, it would then get the new score for this contract by listening to that event. So that is events. That covers some of the major parts of a contract, some of the major areas of Solidity. I'll stop there because I want some time to go on and talk about other things and give us a chance to ask some questions as well. But if you follow the tutorial we have on our website, it goes into lots more detail, and there are plenty of other good tutorials as well. So let me stop that one and go back to my slides. Okay. I'll not go through the best practices. I will just leave them there. There's a lot of practices around security. You really have to be very careful about security. Many millions of dollars are lost every week because of bad security and vulnerabilities in applications in smart contracts on Ethereum. So be very, very careful. OpenZeppelin is a project that provides libraries for you. So please use them rather than reinventing the wheel. They have things like ownable. So all of that I just showed you about only owner, they have done that into a library. So you don't have to write all of that. I did that to show you how it works, but you don't have to do that yourself. You can use those libraries. It has more elaborate permissioning through access control as well. It has tokens, the common tokens that you want, the ERC20, ERC721, etc. They're available as libraries. If you want to interact with contracts, you have to then use other libraries such as Web3.js. These are JavaScript libraries that allow you to talk to your contracts, to allow you to call the functions in your contract. And they're available in JavaScript, but in other things as well. Web3j gives you Java. There are Rust versions, .NET, PHP, lots of other things. Once you've got familiar with Remix, if you want to move on to other development environments, a good choice is Truffle from Consensus. This has been around for a long time. It allows you to do things like run unit tests. It's command line, but it is, once you've got familiar with Solidity and the development process, it's a great next step. Something similar to that is Hardhat. It's fairly similar to Truffle. One great advantage is that it allows you to put log statements into your smart contracts. But have a look at that, have a look at Truffle. They're both good tools. Just quickly, some tips for hackathons if you're doing projects. Think about feasibility and scalability of your application. With Ethereum, scalability can be a problem. With smart contracts, that can be a problem. So you may need to think about that. Something that's very often missed is user experience. Often blockchain projects are written by developers for developers, and they don't really think about the end user who may not be familiar with blockchain or have a technical background. So it's a good idea to have a good user experience there. And then also universality. If you've got a project for a hackathon, is that going to be applicable universally? Are there some barriers to adoption because of cultural issues or maybe technological barriers? That's worth thinking about. Yeah, we have a website that gives you tutorials, so please feel free to have a look at that. If you want some fun with Solidity, you can play our Capture the Flag application, which gives you some vulnerabilities and you to find in Solidity code, so you can play that game. These slides are available at that link. It's now probably a good time for me to take some questions. Okay, so let me have a look. Oh, there's lots in chat. Okay, right. I'll try and go through them in order. Okay, I've answered some. Yeah, so I've got URL for Remix. About IPFS, yeah, IPFS is a great solution. Storing data on Ethereum is extremely expensive, so you really should only store the minimum amount, and there are also issues around privacy as well, GDPR, etc. So it's best to look for other solutions to store data. IPFS is a good solution. It's a decentralized storage, file storage system. It is a very common pattern that people will store data on IPFS, get a link to that the data that they've stored there, and then put that in a contract on Ethereum, so that you can then, there's an application that can then move easily between a contract and then the data that the contract might need. So can a contract be updated if deployed to IPFS? Contracts are not deployed to IPFS, they're deployed to the Ethereum mainnet. If you update data on IPFS, then that effectively has a new address. So be aware of that. Contracts on Ethereum are not updatable. If you make a change to a contract and deploy that change, that becomes a new contract instance on Ethereum. There are some solutions to upgradability, but they're more complex. I don't have time to go into them, but there are lots of resources out there around that. OpenZeppelin have libraries for that as well. Yes, there's plenty of resources around, and there are books available around smart contracts and how to design them, certainly. Oh yeah, there's the upcoming Filecoin sessions. Yeah, I'm really looking forward to those. So they'll tell you everything you need to know about IPFS. Yeah.
Yeah.
So
I've just put a link to the first event in the IPFS or the Filecoin Club, which is starting on Tuesday next week, if anyone wants to come along to that as well.
Great. Okay, I think hopefully I've covered all of the questions on chat. If there are any other ones, I'm happy to answer those.
I believe we had one just come in.
Okay.
From Rashid.
Okay. The two functions you create a return function one, why the other? So the two functions I have, one is a view function, which returns a value. So someone can read from the contract and they'll get the value directly back straight away. The other function where I'm setting the score, that updates the state of the contract, that's a write function. Even though you can return a value from that function, and say if that function was called from within the same contract, then the calling function would get that return value. But if you're calling that function from an external place, such as a website, that return value effectively gets lost, so you don't see it. And that's why we use an event instead, so that we can see that that function has completed, and we can see that our code, that the score has been updated. Data on Ether is expensive. Which is the cheapest? IPFS is cheap. Yeah, effectively free. Well, there are providers around that. But yeah, storing data on Ether is prohibitively expensive. I mean, ridiculously so. So really only store data in your contract that you absolutely need to have in there. Yeah.
Just had a question, direct message asking why the environment was JavaScript rather than Solidity on the Remix IDE.
Okay. Oh, right. Yes. So that's a little confusing. So yeah, the JavaScript is nothing to do with the language that you're writing in. The JavaScript there it's JavaScript VM. It's just a virtual machine which was written in JavaScript, I guess, which runs in the browser. So yeah, ignore the JavaScript part. You don't have to know what language that was written in. Think of that as the browser virtual machine. That's all that is. Yeah. So it's nothing to do with the language that you are writing or compiling in.
So, man, we can conclude with a question from Abraham. Do you have any recommendations for books about smart contract design that you could recommend to the community?
I don't for books, I'm afraid. No, I know there are a number out there, but I couldn't really recommend any. Yeah. I'm sorry about that. I don't.
No worries. Well, it looks like that is all of the questions that we have asked. So again, thank you so much, Laurence, for the second great introduction to blockchain event. And I believe George did just post the 2 links to our upcoming workshops as a reminder. Next week on the 9th, we have on the 7th, my apologies, we have the second Stellar workshop which is how to get started developing in Stellar. And then the following week on the 12th, we have the first Polygon workshop, which will just be an introduction to Polygon. So be sure to come along to those. And as another reminder, this event was recorded and should be up along with the slides on our Medium page and our YouTube channel tomorrow. So yeah, again, thank you everyone for coming out today. Looking forward to see you on future events, and have a great evening, morning, afternoon, wherever you may be. Thank you.